Welcome to all in Examrace. This is the quantum mechanics and we are here for one-dimensional Schrodinger equation free particles. In this we will see the one-dimensional particles for the Schrodinger by using the Schrodinger equation. And that one-dimensional particle is having the finite potential and the infinite potential. So finite potential and infinite potential, we must come to know about the difference between them and how to deal with them, how the Schrodinger equation can be applicable, how the general solution can be right using these different potentials. So we will also solve the question related to these. So we start with the infinite potential. For this we consider a particle is a particle of mass m, and it is defined in a certain region, and that region you can understand in this way, that this is the x-axis and this one is a y-axis. Actually the y-axis is the axis along the axis of the potential, and that potential is a function of the x, and it has certain boundaries, means the particle is in between, the particle of mass m is in between the square well, which has certain boundaries, and that minimum value or the value of x is minus a to x equals to plus a. So this is the, you can say, the potential well. And what is the height of the potential well? If we say it goes to infinity. Okay, so height of potential means potential as a function is either 0 or infinity. It is 0 when x is less than a. So if you see this, x is less than a, okay, then it is 0, means it is inside the well, and when x is greater than a, mod x is actually greater than a, then it is at infinity. Clear? So this is what we can say, the potential well. Now we just define in the three regions, first, second and third. First and third region are outside the well and second region is inside the well. So it's a one dimension infinite square well potential. Now what we will do, so we will write the Schrodinger equation. Okay, Schrodinger equation for these three regions. But what about the second region? Because second region is a kind of a special region. So the particle, you can say, exists only in the second region. When we talk about first and third region, particle, you can say the potential is 0. Okay, so the region takes the infinite potential, hence the first and second was first and third is not going to be possible, because the second region is potential is infinite. It has chances that the particle is inside between the minus a to plus a, but there is a no chance that the particle is at the region 1 and 3. Okay, so we require to solve the equation that is related to the region 2 only. For this we will write the Schrodinger equation. Okay, Schrodinger equation. And for the Schrodinger equation, you know very well what is the Schrodinger equation. It's actually d2, and I'm writing it for the second region. Okay, especially for the second region I'm writing it. So it is d2 psi over dx square plus mass of particle is m, so 2m over h cut square times e minus v. Okay, and its psi equals to 0. Now as you know, inside the second region potential is 0, outside there is an infinite potential, so no chances the particle is there. So if it is the second region, this is the basic thing about the Schrodinger equation, but for the second region b is 0, so I can say that if b is 0, my equation changes to d2 psi over dx square plus 2m e over h cut square times psi, which is equals to 0. Clear? Now we have the Schrodinger equation, and we can say, let, you can say here, let 2m over h cut square, 2me over h cut square, let this be the k square. And if it is a k square, my Schrodinger equation get modified, and this changes to k square psi equals to 0. Clear? Now we move to the general solution. General solution for this differential equation. Okay, so although we can say that your psi is going to be as a function of x, and if I write the general solution, it's going to be the sine k of x plus b times cos k of x. As you know the value of k already, so this is the general solution. Now, so first step was to write the Schrodinger equation. Second step to write the solution of the Schrodinger equation. Third step is to write the boundary condition. So if I write the boundary conditions for this, then you just look at the figure. Again, this is x, that is y is v of x, and you have a reason x equals to minus a to x equals to plus a, and it is from this reason. You understand this very well. Whole story is about the boundary reason here. So if you see the boundaries, just talk about x equals to a and x equals to minus infinity, your potential get vanished, or you can say function, sorry, the function get vanished, or you can say potential is touching the infinity. Okay, so function get vanished, so what we can say, x equals to a psi, the function is vanished, so you can say 0. Just apply the boundary condition here, okay, in this equation. So if I apply, I can say psi of a is equals to a cos ka plus, or actually it's a sine a, okay, a sine ka plus b cos ka, but it must be equals to 0. This is the, you can say, one condition. Okay, another condition, you know that at minus a it is